Hello, everyone. Today we have two guest speakers from Cognitive Learning and Robotics Laboratory at Boğaziçi University, led by Emre Uğur. And today, Mete and Yunus will talk about some of their recent work on learning from demonstration, where their main goal is actually about trying to generalize or adapt to some out of training data distribution. So hello again and welcome to our seminar series. Yeah, the stage is yours.
Thank you. So I will start. Hello everyone, I'm Yunus Seker and I'm a PhD student working at Boğaziçi University Colors Lab under the supervision of Professor Emre Uğur. First of all, I want to thank Akbulut for inviting us for this week, and thank you all for coming here to listen to us. Today, me and my friend Tuluhan will be talking about learning from demonstration with deep learning and adaptation to the outside of the training range. The topic is heavily related to robot learning, but I think the base model that we used in our work or the transfer learning algorithms that Tuluhan will mention later are highly related to the most of the machine learning areas and can be useful. So let's start. Okay, so this is the outline of the presentation. We have two parts at the start. I will talk about learning from demonstration and what are the challenges in learning from demonstration. And then I will introduce you our method, namely conditional neural movement primitives, which is published in RSS. And at the second part, my friend Tuluhan will be talking about his work, which is adapting this learning from demonstration framework to the outside of the training range. So let's start with an introduction and the question of what is learning from demonstrations. So learning from demonstration is actually a very straightforward concept that we may all know, because it is one of the most basic learning methods that humans and animals use every day. So it's also a very popular supervised learning method in robotics. So basically, in order to learn a skill, an agent uses the information called a demonstration that is provided by an expert to learn a skill model. Then by using this skill model, the agent can reproduce the skill whenever it needs it. So there's a difference between learning from demonstration and exact imitation, which is the learning model here. Imitation means that the agent replaces the exact information that is shown by the expert, but learning from demonstration means that agent learns an underlying representation of the skill that allows it to generalize the skill to different configurations. So here I want to start with a list of popular challenges in the learning from demonstration area. So one by one, I will go through them, and also I'll try to give some examples from real life for each item in the list. The most basic challenge is to learn a distribution of movements of multiple demonstrations. So our method should learn from multiple demonstrations because, as you can see here, for example, it shows 9 ways to hold the wine glass, for example. Because basically there can be multiple ways to do an action without any explicit reasonings. And also there can be multiple modes of actions in the demonstration set. So we can say that a mode is a group of actions that are similar to each other. So in this case, for example, there can be 2 modes of holding glass which are with left hand or right hand. So the next challenge is to learn complex motions from task parameters that have nonlinear relationships with motor data. So let's define what task parameter is. So we say that a task parameter is any kind of information about the environment that is given to the system explicitly. For example, the height of the object here can be our task parameter, let's say. And about the nonlinearity case, I want to give this example here. So let's say that our task is to find a robot position in order to grasp this object. But if we were using Cartesian coordinates of the endpoint of the robot, the task would be linear because Z coordinate information increases linearly with the height of the object. However, when we use the joint values of the robot as our data, the task will be non-linearly related to the height of this object because of the kinematic calculations. So this is another challenge in our talk. So the next challenge is being able to discover task-related features that are not explicitly given, but hidden in the sensor motor data. So this is a hard to tell concept, but I think the easiest way that I find to talk about is this watermelon example. So let's say that you are given a task to pick the sweetest watermelon in the market, but you can't cut all of them open to see how red is inside. However, as you can see here, there are some hidden features on the watermelon to help us to understand how sweet it is, such as size or spot color or stem type, as you can see here. So just like in this example, when we want to learn from some demonstrations, there will be hidden features in the data that actually gives information about the characteristics and underlying reasonings of the movement. And so in the end, we need our learning method to find and extract this relevant information in demonstrations. So the next challenge is being able to learn complex motions from high dimensional data. This could be like force readings, or the most popular one, as you can see here, visual readings. This is one of the most natural requirements because how learning from demonstration often works in humans. So yes, humans mostly use visual data to learn the demonstrations of others, but in robotic area, unfortunately, we saw that this is actually a problematic case because most of the recent work have no structure to use images in their frameworks, or because like they have huge complexity issues and they are using high dimensional data. So in our case, finding a model that can handle this high dimensional sensor motor data is one of the most challenging problems. So the last challenge that I will talk about is being able to adapt to the environment changes during the execution of the movement. Because as you can see here, for example, the real world and the environments that our robot can be placed in are changing continuously. And humans have this ability to change their actions according to the environment very quickly. So we need our robots to learn a model that allows them to adapt to the changes quickly on the fly. So all of those were the popular challenges in learning from demonstration. And we should say that there are multiple methods and frameworks that can solve these challenges, but separately, they can solve them separately here. Our aim is to...
Yunus?
Sorry.
Hi, Yunus. This is Çağatay.
Hello.
So I didn't understand the last item. Like, how is it related to the earlier items? Like adapting to environment changes on the fly. That seems like a little different than.
It also seems like on an issue on the maybe controller side, but like in here, like in a general way, I tried to collect all of these challenges together because my point here is that like all of these challenges are solved in different methods and algorithms, very well working algorithms. But in our research, in our paper, our aim is to handle all of these challenges with by using a single framework. So that's why I put it together with others.
Okay, thank you.
So before we dive into explain our method, I want to talk about here the reason behind it. So in our work, we will be using a neural network architecture. So I wanted to talk about why we prefer to use a neural network architecture compared to the other classical methods. So first, We should say that the classical methods in the learning from demonstration area, as we said earlier, are stable and they are working robustly, and they're actually secure to use in practical applications compared to any other neural network applications. However, the technology is developing, and we are able to collect more complex data from experts, and our robots are now becoming more capable of performing complex actions. And as the actions become more and more complex, the classical methods start to become shorthanded because complex motions require handling high-dimensional data, and they require a system to have a better understanding of data, such as autonomously extracting features from the complex input data, as you said. So because of this reason, we see that the classical methods start to fail in today's some of the challenges. So this basically pushed us to search on a modern method that can handle those difficulties. So
yes, I have a few challenges for you. Can you go back to the previous slide?
Okay.
So like there are methods that use like dimensionality reduction with classical methods. They can learn latent representations, right? And this is like Kalinion has been doing this for a while. Mixing behaviors, you can mix behaviors like probabilistic movement primitives. You've already touched upon that, sorry about that. But you can also mix other types. So I have a hunch that like you can check most of these with classical methods and as well as be stable. So this is a challenge issue to you and maybe the other speaker at the end. Can you demonstrate like a crucial skill that can't be learned by a classical method where it can be learned by your neural network? By the way, I was in Yunus's thesis defense, so I know it.
Yeah.
I'm also using information from the future to issue this challenge. That's it. Like it's by the end of the slide. And I'm sure you have an example. That's why I asked it. Yeah, I mean, you can do it later.
For now,
like,
I don't think I have an exact example, but like the idea in my mind is that, like, as you said, most of the classical methods also working on these challenges, but like from the start of this research, my idea was that by using a single framework, addressing these challenges in any need when it comes to a challenge as a challenge to you. So
I mean, I can.
And then my idea was that I can use this approach by not looking at the challenges at all, and my framework can solve it without any need of me, any explicit need of me. So most of the other methods, yes, most of the other methods require other complex like pre-processing or post-processing or whatever specific to the challenge itself. But my idea was that using this framework from end to end, and then it autonomously create a solution to those challenges. Yeah.
Instead of adding other stuff to a pipeline, like using different methods, you say one end-to-end approach solves everything. That's what you mean?
Yes.
Okay. Yeah. Also, maybe I can add something. So in my work, I had an experiment where Jan Peter's group tried to condition trajectories with task parameters. So as you said, it's possible, but additional mechanisms are needed. For example, they couldn't do it with using only ProMPs, but they had to add Gaussian processes to map these task parameters to trajectory parameters. But like at the end, because neural networks are great function approximators, so like our method was able to handle this mapping more sample efficient than theirs.
So yeah, as another like example, so I can say that, for example, classical methods.
Okay, I think I derailed the conversation. Maybe we can have a discussion at the end about this.
Okay.
Yeah.
So I will continue from here. So after our research, we find this method called conditional neural processes, which is a new conditional learning architecture that works similar to the Gaussian processes principles. And we use this method as our base model. In their paper, they show some simple experiment that method is able to learn sequential function distributions, which we will extend and propose a model to use on complex sensor motor values. So what CMPs do is basically combining the advantages of Gaussian processes and neural networks. So let's start first. Let's talk about Gaussian processes. As we know, the Gaussian processes collect samples and observations from the data and learns conditional probability distributions over the other target values. But two main disadvantages of Gaussian processes are, first, you have to define a prior distribution over the data. And also the complexity of the algorithm is very high, that goes up to like n plus m over 3. So this is where neural networks become useful, because we don't need to define a prior data if we use neural networks and encoders. And the architecture itself will reduce complexity because it's only a forward pass. And the model is much simpler. So there are two things I have to mention before we look at the architecture here. The first one is permutation invariancy, because in Gaussian processes, the order of the sampled observations do not matter. And the second one is obviously our model should be scaling to multiple observations, because in like Gaussian processes, they can handle multi number of observations as well. So the solution to these two problems we will see here are using a parameter sharing encoder and a symmetric operator. So let's look at the architecture. It consists of 3 parts. And here, let's assume that we want to learn a function f from x to y. And we know the corresponding values of f, x1, x2, and x3. And we want to know that given those values, what could be the value of f, x4. So we adapt this model to construct a framework in order to learn from demonstration. We can also give some details here. So in the first part, you see the sampled observations, which are x and y's together from data. They are sampled. So each of these observations are passed through this parameter sharing encoder to get their latent space representations. So all of these encoders are same. So after getting this representations for each observation, they are merged into one representation here by using an aggregation operation. So the reason of this operation is to make the model to be able to handle multiple observations, as we said earlier, and as the number of observations in every step can be changed. So after that, this general representation and the target value x4, let's say, in this case, is together used in a decoder in order to get a prediction for fx4. So here I want to directly go deep into our proposed method and explain all of this in terms of sensor motor values or robotic terms. So in the upper side of the figure, I will explain the training of our model, and below side I will show that how we can regenerate sensor motor values in test time configurations. So let's start with our demonstration set here. We define our demonstrations as a function from time to record the sensor motor values. So in this figure, of course, the sensor motor value is a one-dimensional vector, but in practice, it could be any multi-dimensional data like endpoint of a robot's hand, or joint values, or force sensor data, or even images. It can be like any combination of it also. Okay, so let's continue. So as we said, in each training step, a random demonstration is chosen from our demonstration set. And then a number of random time and sensor motor values are sampled as observations from this selected demonstration. And in addition to that, here, as in the blue, a random target time step is also chosen. So the aim of the system here is to predict the value of this time step given this observations. So the next step, the sampled observations are passed through a parameter sharing encoder to get their representations here. And then these representations are merged into one by using an averaging layer in our case. But here, any symmetrical operation can be used. Yeah, so in that we have this general representation, and it holds the information for all the observations at the beginning. So here the general representation is concatenated with the target time step and passed through a query network, which is another basic decoder structure. And in the end, we have a mean and variance prediction of the sensor motor value in the target time step. So to train our system, we calculate the log probability of the ground truth sensor value on the predicted Gaussian distribution here. And we backpropagate the minus of this value. So it's basically a probability error. So we repeat these steps again and again with different samples, with different observations, different target time values, and different observation numbers, and so on. So in the end, the network converges to a point where it learns how to make conditional predictions on any observations and any target time step. So this was the training of our system. So what happens in the test time? So after the training, instead of sampling sensor motor values from our training data, here we define novel observations as our goals to be satisfied. These observations can be starting or ending points of the robot or any intermediate condition, or they can also be the online position and sensor readings of the robot during the trajectory execution. So for example, in this case, there are start and end points. So let's continue with them. So as we did in training, we passed this start and conditions as observations to the encoder, and then averaging layer, and in the end, we have our general representation. And once we have this general representation here, we can query the system with all time points from 0 to 1. So in the end, we get mean and variance predictions for whole trajectory. So for example, here you can see the visualization of the predicted trajectory. And after the calculation, after these calculations, we can give this prediction to the robot controller in order to execute the movement. So a good point here is during the execution, we can change the given goals or any online readings of the system, and the CNMP can predict trajectories according to observations dynamically, and then change the prediction on the fly during the execution. So here we had 6 experiments to show that our system is able to handle all of the challenges in the beginning. But I think I will go over 3 of them because of the time. So in every experiment, I will try to show the challenge related to the experiment and then introduce the task and the results. So in this first experiment, it's a tabletop object avoidance scenario. It's a basic one. And the challenges here is to see if the CNMP can handle multiple trajectories and it can discover the different behavior inside of the data by itself. different modes, as we can say. As you can see here, we placed an object on the table, and the aim of this experiment to move the robot's endpoint starting from the left side of the table to the right side. And as you can see here, these 2 points, the robot's endpoint avoids the object by passing through these 2 common points according to its starting position. So it starts if it starts with a positive value, it goes from upper side, and if it starts with a negative value, it goes from below. So the important point here is that we do not give any information or any label to our system to make it understand this is up or this is down, like any type of mode or any type of relationship. Just give the time and 2D position values, and we expect our model to form these 2 different modes of representations by itself. So in the end, we train our model with these 6 demonstrations. And so this page shows the test results. So in this part, we compare our model with state-of-art learning from demonstration method called probabilistic movement primitives. So here the black dots are the test time conditions that we want our model to produce a trajectory according to it. So as you can see here, in the first example, when both models are conditioned on this common point, they both can give successful results. However, when condition is given at any other points, ProMP cannot successfully produce a trajectory that also avoids the object in the middle of the table. So the reason why ProMP tries ProMP fails here is that ProMP tries to learn all of the demonstrations in a single distribution. But on the other hand, we see that CNMP can separate the distribution into 2 modes and understands the reasoning behind the mode selection. So when we condition it from below, it creates a representation for the demonstrations going from below, and it produces a movement primitive according to it. So
Yunus, regarding to previous slide, like you mentioned that probabilistic MP cannot differentiate going up or down kind of thing, but CMP, yes, I guess it does differentiate. So, I mean, if it is explicitly told, ProMP that there are 2 different distributions somehow, would it also work successfully or not?
So, as we said earlier, like if this was a task with also including task parameters, and let's say that these 3 demonstrations are labeled as 0, and these 3 demonstrations
are labeled, I meant.
Like 1, exactly. And we construct the ProMP framework with this task parameters as well. And then in the test time, we also say that this is like one label 1 primitive, and this is a label 0 primitive. It achieves the given result. But as I wanted to mention earlier, that like CNMP do not need to be told this explicit relationship. It finds it itself by looking at the data.
How does it do that? Like I listen to your talk, but I miss it. Like how does it do that? Like, what is it? CNP different exactly from ProMP?
So for example, I can turn back to the model page here. So we investigate why it can differentiate these 2 modes, and this is like the encoder part, and the representations are constructed here. And in the representation space, we did some visualization there, and we see that the CNMP can divide these representations into 2 clusters. Where the upper side demonstrations are clustered one side of the representation space, and the other below demonstrations are clustered on the other side of the representation space. So as a summary, like this encoder and representation learning part helps the framework to differentiate between different characteristics of demonstrations, I can say.
So how is this different than labeling? I mean, like how? I mean, I'm trying to understand. I'm not an expert.
This is
how is it different than the labeling, right?
So this representation clustering is learned by the framework itself. Like in this way, we do not give any explicit label to the framework to say that this is an upside demonstration or this is a downside demonstration. The encoder itself extracts this information by looking at the outputs, as I can say. But in the earlier example, in the ProMV example, you explicitly give to framework that this is a label 0 demonstration and this is a label 1 demonstration.
So if I combine like ProMP with some classifier, would it give me this similar performance or not?
So
somehow, if I can combine ProMP with some classifier, like the way that
if you can, like, but in this case, you have to like explicitly tell how many clusters there are. For example, if you're not controlling your classifier, there can be 6 demonstrations labeled differently on 6 different clusters. Like there's no automatic reasoning behind it, I think, but maybe also you can do it with another improvement also. But yeah, if you like explicitly put some another methods and algorithms in the classical methods, yes, you can handle these challenges. But like as my like general point from the start, in our case, you do not need to explicitly tell anything, because the network itself can extract these features by itself.
Okay, thank you.
Thank you. So this is the second experiment I want to show. So we tested our system with a high dimensional sensor motor space scenario. So the task can be seen here. This is a top-down image of a room. The task is starting from a point at the left side, and by avoiding the red obstacles, going to a final point at the right side. So in this experiment, the starting, ending points and the lengths and positions of these red obstacles can be changed. So we produce 1,000 room configurations with different scenarios and provide solutions to every configuration with a basic heuristic, as can be seen here. So on the right side, you can see the neural network architecture. The framework is the same. The only difference is that in this case, we will be using these pixel coordinates here. And we embed the room image to the network by using a convolutional encoder. So we trained our system with these demonstrations and with this architecture. So let's see the test time predictions. Here you can see the results. You can see the test configurations of the rooms and the condition points as the white stars here. As you can see in the first row, when different start and end points are conditioned in our system, it can produce away from starting point to the ending point by avoiding the red obstacles. Like in the second row, another interesting feature can be seen here. So here the conditioning point is the same in all of the 3 cases, but the time value is increasing slowly. The conditioning time pointing is increasing slowly. So as you can see here, our framework shifts the starting point to upwards in order to satisfy the time condition. So this is, for example, t equals 0.6, and it shifts the starting point to upside in order to delay the time and satisfy this time configuration. But in the earlier time steps, it goes from, it starts from a closer point in order to get here faster, for example. So here we just convert the 2D model into a 3D simulation scenario. So the aim is the same. The robot tries to carry the ball to the right side without hitting the red obstacles. And the scene is captured by a vision sensor, as you can see on the left top side. So in this video, like obstacle positions are dynamically changed during the execution. And our model can produce new trajectories according to the changing positions of the obstacles and like directly adapt to the changes on the fly.
Excuse me, so you mean that there is a visual feedback giving to the controller?
Yes, yes. There is a vision sensor looking at the table here. I don't know if you can see the
yeah, I can see.
Scene, the picture in the left upside. We condition the system simultaneously when it is working with the current configuration of the scene. Like we simultaneously capture the room configuration and then.
Okay, I got your point. But how do you exactly understand the position of the obstacles? So how do you estimate them in real time?
Yes, so there was no. I'm sorry.
I'm asking about how are you determining the exact position of the obstacles? Have you done it in the real world or it's just a simulation?
So in this experiment, we worked with images only, and there is no obstacle position information given to the system. We generate different room obstacle configurations in the simulator, and then just with a simple heuristics, we created some expert demonstrations for that.
I got your point. I'm asking about another issue. Yes. Let me clarify. So you say that we are trying to understand the position of the obstacles in real time, dynamically on the fly. So what I'm asking is that what is your plan to do it in the real time? For example, when you are experimenting in the real position, the real world, there is no simulation that you can understand the position of the obstacles. Then what I'm asking is that what is your plan to do it? How are you going to understand or estimate the exact position of the obstacles in the real world?
So
using
that camera, it is same with this experiment. In this experiment also, we do not give any explicit position of that obstacles to the system. We just give the image to the system, and besides the next to image, we also have this solution of the robot in terms of, let's say, X, Y, Z coordinates. So it learns the X, Y, Z solutions, coordinate solutions, in terms of images only.
Yeah, so
by looking at other images, it can also extract coordinates for itself.
So you mean that you just take a picture with a simple camera and using that picture and feeding it into a CNN or something? Yes. You understand the positions of the obstacles?
Yeah, I mean, it does not have to understand the position of the obstacles. Actually, I don't know if the model directly understands the positions of the obstacles, but it can learn the relationship between these pixels in the image with the solution for the robot's coordinates.
Okay, so
it should learn the position of the obstacles related to images, but there is no explicit obstacle position.
Yeah, exactly. So if you don't have the explicit position, so how are you going to program the robot?
Yes, with the images and the like convolutional encoders. And so you just take some image you just take the configuration of the obstacles as an image, and you know the time and position solution for the robot, right? Yeah. For that image. Mm-hmm. So you train your system by just this image, and this is the solution. Mm-hmm. Find the relationship between them. So in the test time, if I want to change the image, you can produce me.
No, I got it. Thank you very much for the clarification. Thank you.
Thank you. So this is the third experiment. So our aim is to test our system on learning nonlinear relations between the parameters and the sensor motor values. Here, the task is the object is placed on the left side of the table, and another object, which is a wall, is placed in the middle of the table. The heights of these objects are changing as task parameters. The task here is to take objects from the left side and without hitting the wall object, putting it to the right side. Here, our demonstration data is consist of 6-dimensional joint angles instead of the end position. And our task parameters are the height of the object here and the wall. So in this example, we give the height of the wall and the object explicitly to the system, and we expect our system to understand this nonlinear relationship between wall and object height and the joint angles. So this is the aim of our experiment. So here you can see the training demonstrations with different height configurations. So the object height is ranged from 2 to 6, and the wall height is ranged from 2 to 8. And we trained our model with these 8 trajectories. So after training, in the test time, we test our system with the novel parameters that are inside of the training range. So this is an interpolation case. As you can see here, our framework can produce trajectories that successfully accomplish the task. And on the right side, you can see some joint values with blue dashed line is test ground truth, and the red line is prediction. They are almost like on top of each other in the interpolation cases. So after that, we test our system with the parameters that are out of our training range. So as you can see here, our framework can produce like meaningful trajectories up to some point, as in the first example, but it starts to fail after that. So here, like we say that this is like not only a problem that is specific to our method, but it's a general problem for most of the neural network architectures. And actually, Tuluhan will talk about this problem and how we like propose a solution to that later. As you can see here, like when the parameters are going outside of the training range, it starts to fail. So in that experiment, what we conclude is that our framework can also extract this nonlinear relationship between the wall height or the object height between the 6-dimensional joint values. But we had this problem of extrapolation cases. So in the end, as a conclusion on my part, we can say that CNMP can handle nonlinear high-dimensional multimode learning and can react and adapt to the changes during the execution. But as one problem of our framework, we can say that it cannot well generalize to the extrapolation cases due to the nature of the neural networks. So, so this is it for me. I will leave the screen to Tuluhan, and I think he will continue to talk about how this framework can be extended to adapt to the outside of the training range. And thank you for listening to me. I think.
Very nice talk, Yunus. Thank you very much.
Thank you. So I think I'll stop sharing. Yes.
Hello. So I think our time is limited. I will try to be as quick as I can. So I am Tuluhan Akbulut, a master's student from Boğaziçi University, and we are from Colors Lab with Yunus and Ahmet, and I'm co-supervised by Erhan Ostop, and you're supervised by Emre, and I had one collaborator from Germany, Hongo. So it's my pleasure to present our work here. I would like to thank again Aykut Hoca for the invitation. So we use learning from demonstration to teach robots dexterous skills. So as you listened earlier, the performance depends on the demonstration distribution. Let's assume that 6 demonstrations are given to an LFD model. So after training with these demonstrations, when the model is requested with the black dot to perform the skill within the distribution, it can generate the required trajectory. However, if the required trajectory should follow a path outside the distribution range, task requirements may not be satisfied and further adaptation is required. So, so this simple example may be a problem for neural networks, but like in general, of course, like the performance depends on the demonstration distribution and we need adaptation. So let's have a look at the challenges. So in this work, we study adaptation during task extrapolation through trial and error and skill transfer. The relations between task parameters and trajectories are often highly nonlinear and complex in real-world problems. Therefore, excessive policy updates may be required for adaptation. However, experiments with real robots takes time and resources. We have to be efficient. Another challenge is preserving the demonstrated behavior because it can be more practical than to encode these behaviors in a reward function. These behaviors can be related to safety, robots and environment constraints, or any other user preferences. And the third challenge is skill transfer between robots with different embodiments, because this thing is extremely difficult when it happens between robots with different morphologies. In this case, additional engineering efforts are required to find correspondences between policies. So in literature, state-based correspondences are sought, but to do that, we need explicit state pairing. So we want to overcome this hand engineering with our framework. So our proposed method called adaptive conditional neural movement primitives. So it's continued work on top of CNMP, where we combine it with a reinforcement learning agent. So it's the base LFD model, and Yunus already talked about it. So I will skip this part. So the important thing that I want to explain is that given that observations, the encoder network finds the corresponding representations for each observation point, and at the end, with this average operator, we obtain the representation for the trajectory. So it's a feature that I exploit in this work. The second important thing is that so the neural network can handle the mapping from task parameters to trajectories quite well. So in order to achieve the goal with given task parameters, CNMP model is conditioned with these parameters to generate the required trajectory. Then the generated trajectory is given to robot execution. If the robot does not achieve the task, the reinforcement learning agent is triggered. As you can see, there's a fail mode here. So the RL agent initialized with the LFT model. It has the same structure with the CNMP. So this network updates its internal parameters via reinforcement learning, which is alternated with error-based supervised learning. For observation and task parameters coming from these demonstrations, supervised learning loss is used to update the network. When the inputs are coming from extrapolation cases, the same network is updated using policy gradient loss. In practice, this allows the system to generate novel trajectories that are encoded into the same latent space with demonstrations and share similar characteristics with them. After RL agent finds the satisfying trajectory for the new task, this new trajectory is fed back to the LFT system as a new demonstration. Afterwards, the loop continues and our framework improves itself at each cycle and becomes less prone to failure because we enhance the demonstration distribution with novel trajectories. In skill transfer scenario, both robots have their own SNMPs and they form a common latent space during learning from demonstration. Here, an additional mean squared error loss is defined to make corresponding representations similar. Our representation learning method can handle different number of joins and different number of observation points because it finds the representations at skill level. Therefore, no time warping or explicit state pairing mechanisms are required. In this part, task parameters are not used, not to involve any bias about the task. So we are dealing with only agent, like states about the agent, not the task, not to include any bias. So at test time, skill transfer for a novel task can be achieved by transferring the skill representation from the first robot to the second robot. Afterwards, the target agent can perfect this skill using its RL agent. So I will quickly go over experiments. So this experiment is similar to the first experiment of Yunus talk. Here the aim is to extrapolate to a novel wire point outside the demonstration range. LFT on the model cannot generate a trajectory that goes through the specified point. RL-only model generates a trajectory that maximizes the reward, like a trajectory that goes through the wire point, but does not preserve the demonstrated shape. But our framework achieves the task while preserving the demonstrated shape. So here we see the latent space representation. So from the figures on the right, we expect that of the novel trajectory would be somewhere here, like the dot showed with magenta. So without this optimization with reinforcement learning, sampling from this latent space does not produce a meaningful trajectory. But at the end, we see that our framework can encode this novel trajectory to the right spot.
Hello. Ne yapayım ben şimdi?
Sorry? Okay.
You can continue to learn.
Okay.
Yeah, sorry, my bad.
So, in order to evaluate our model's adaptation capability to novel goal points while controlling a robot, we adapted this experiment from Stark et al. And compared SCNMP with their state-of-art policy adaptation method. So their policy adaptation method is implemented on top of ProMPs. So there was a discussion about that. So I have to say, I would like to say a few things. So in this experiment, 9 demonstrations of pushing black obstacle to a goal point are provided to a 3 degree of freedom planar robot. Then the robot is requested to push the black obstacle to a novel goal point. So it's hard for ProMPs to find the posterior distribution given the task parameters. So somehow they should like classify or cluster trajectories, and like then they should find correspondences between task parameters and trajectories. So this is not easy, but we will see it's achieved additional mechanisms. So here in this work, they had to use a single ProMP for each goal position. However, our framework can use one model for all goal positions. So on the left, demonstrations are shown. And on the right, you can see the pure LFT performance for extrapolation and performance after adaptation. Shown with the blue dot, our model finds the successful trajectory or requires small adaptation for all interpolation goal points. For the extrapolation goal point, SCNMP achieves the task around 60 iterations. As shown in the table, SCNMP requires order of magnitude fewer samples than the baseline to adapt. In the third experiment, the aim is to evaluate our model's adaptation capability to novel environments. This experiment is adapted from Everton et al. For comparison with their adaptation method. The aim is to produce a trajectory that starts from the fixed blue point, avoids randomly positioned vault, and ends at the randomly selected red goal point. Demonstrations are given for 30 environments. So here, Everton et al. Introduce Gaussian processes to find correspondences between these task parameters and trajectories. On the left, you can see sample demonstrations, and the performance of LFT-only model and SCNMP is shown together in the video. So we see that the demonstrated behavior cannot be observed for extrapolated goal point for LFT-only model, but here we see that on the right, SCNMP can deal with it. As shown in the graph, the baseline and our method are competitive in terms of the number of environments used. However, if you plot the same graph with respect to sample trajectories used, we see that SCNMP requires many fewer samples than the baseline for each environment. So this table illustrates that SCNMP is order of magnitude more sample efficient than the baseline for a single environment and for the whole task. So we implemented two real robot experiments. The first one is coming from the experiment of CNMP work. So the last experiment that Yunus talked about. So here we illustrate the performance of SCNMP for the failure modes of CNMP. So these object height and vault height are extrapolation task parameters. Second task is a marble pouring task. The task parameters are weight of container and desired pouring amount. Here the challenge is to generate motion trajectories while using a weight-based reward to pour a novel desired amount. And like it's achieved in 18 real-world samples. So the last experiment aims to evaluate the transfer learning capability of SCNMP. So this experiment is adapted from Gupta et al., where two robots with different morphologies are provided with proxy skills to learn how to transfer policies. Given that 3 degree of freedom robot has the skill to achieve a button pressing task, 4 degree of freedom robot should benefit from its experiment and acquire this skill quickly. note that this task is extremely hard to learn from scratch because the robot does not receive any reward unless it can touch the button. So the reward here is the distance between the blue button and the red goal position. Three proxy tasks, reaching, pushing, and peg insertion, are used to form a common latent space. A pushing task is shown on the left. For the task, a demonstration is provided to the 3D growth freedom robot, and 4D growth robot is expected to approximate the skill with skill transfer. So for 12 demonstrations, how common latent space is formed is illustrated on the right. Our model finds representations at skill level, 12 representations clusters for 12 skills. Therefore, it doesn't require additional state pairing techniques because it finds the representation at trajectory level. The effect of common representation and reinforcement learning is shown here. 4D growth freedom robot almost acquires skill after the transfer in the middle, and the skill is perfected with RL agent on the right. So in conclusion, adaptive conditional primitives is order of magnitude more sample efficient than state-of-the-art methods. We were able to preserve demonstration shape by training with demonstrations continuously. And it enables skill transfer between robots with different embodiments by finding a common latent space at skill level without explicit time warping and state pairing mechanisms. So that was the end of my talk. So here are the people that contribute to this work, and you can find the code and data on our project page. Thank you so much for listening to me. Do you have any questions?
Very nice work, very nice presentation. I just tried to understand how it adapts. Can you go back to the slide where you present the architecture?
Yeah.
Sorry that I had to go.
Yeah. No, it's okay. Of course.
Yeah, it's here, this slide. Can you explain in simple terms, how do you handle that extrapolation issue? So I see a point extrapolated, and you label it like a fail using reinforcement learning. What do you do exactly?
So here, so the robot faced a failure. So in the tasks, there's a reward, explicit reward function. So reinforcement learning agent uses policy iterations and policy gradient laws to maximize the reward. So here,
what's the reward? What's the reward in the system? What is your reward in the system?
For example, in the working example, it's going through the waypoint. So it's the distance minus distance to the waypoint of the trajectory. But as I showed later, maximizing only the reward cannot ensure that we will preserve the demonstration shape. And this user preferences are hard to encode in reward function. So on top of reinforcement learning, we also introduce together learning mechanisms. So there are alternating iterations where we use supervised learning laws, and we use demonstrations as inputs. And in other iterations, we use reinforcement learning and maximizing the reward.
So reinforcement is maximize the reward, and you show in the graphs when you just use the reinforcement learning, you don't get a good trajectory, right? I think it was the next slide. But how does it fit into the existing trajectories? How does it make it similar to the existing trajectories? Like, how does it understand the shape of the trajectory? Like, is it trying to imitate the existing trajectories eventually?
Yeah, so it's a...
Yeah, here, like RL only, like, cannot do that, right?
Yeah,
RL
yeah.
only cannot do that.
Yeah.
So how does it make it similar to the existing trajectories?
So it's natural consequences of using this autoencoder framework, like a conditional neural movement primitives. So all trajectories are encoded into the same latent space. So if we can if we can encode our novel trajectory into the same latent space, and like because so they are coming from maybe like a small number of dimensional latent space, let's say 4 or something like that. So this encoding helps us to ensure the trajectory characteristics. So it's the consequence of encoding the RL trajectory into the same latent space with demonstrations. So maybe you can say that there's no guarantee. So like it's a future work in my mind to show theoretical guarantees or like measuring the similarity. But like in this work, so it's the consequence of the underlying framework and like the together training mechanisms.
So maybe I can add something. So for me, it's like a fight between RL agent and the learning from demonstration agent. So the RL agent tries to stretch this representation space in order to extrapolate to the outside of this training range. But in the next step, LFT agent comes and says that nope, you have to like preserve your shape in order to in terms of this given demonstrations, no come back. And then our agents tries to go away like again, and then LFT tries to call it back again, and so on. And this fight eventually causes this representation space to like stretch in a way that it can also preserve the old demonstrations.
Yes, so like we can say that the model tries to find a common solution with the objective and the demonstrations. So because like there are actually two losses. So the first one is encode demonstrations, and the second one is maximize reward. So like at the end, it tries to find the common solution.
Okay, thank you. I really enjoy your presentations. I mean, this is probably the first time that we have seen the robotics-oriented talks, so I'm happy to see that. So I asked too many questions for that reason, but I enjoy it very much. It's very good
Thank you very much.
high quality.
It's a pleasure for us.
Very well presented as well. I think I like it very much.
Thank you so much. I'm really glad that you enjoyed.
Well presented as well.
Thanks so much. It was great to present.
So are there any questions from the audience?
Yes, I have one.
Which
program did you use to make these interactive simulations?
What program did you use? So these simple tasks implemented in Python. So for this task and like for the transfer learning task, we used Copellesim VREP simulator, and I think also Yunus used VREP for the simulation tasks.
So the UR5 simulations, are they done in VREP?
Yes.
Yeah.
Not the ROS, so it's not in the ROS environment. Not Gazebo and ROS. Is it VREP?
No, it's in a VREP environment, and it is connected to a Python and the neural network via a ROS connection.
Yeah, so like we are using VREP via ROS.
Is there any reason why you prefer VREP over like Gazebo in ROS environment?
It was simpler for us.
Yeah.
No, like any other specific reasons. It was like just easier for us.
But actually, like it caused a problem. For example, this experiment in the baseline work implemented in Akbulut, but like I also talked with the corresponding author, but like we couldn't, she couldn't send me the simulation task, like simulation implementation, and like she couldn't also make her model work in my environment. So maybe we should switch to a more used simulation framework. I don't know.
Okay. Any other questions?
Yeah, can I ask a question?
Yeah.
In your last experiment, you have different amount of joints for that robot, right?
Yes.
That's the problem.
Mm-hmm.
So you have different amount of outputs for your models, as far as I understand.
Yep.
So your RL model and the observation model outputs different amount of joints. So they're not the exact model, but they share some hidden representation.
Yeah, so they share the representation here, the R1 and R2. So inputs have different dimensions, as you said, and also outputs also have different dimensions. But like I can design the neural network that their latent space will have the same latent dimensions. So then I can like introduce a loss to make these latent spaces similar. So regardless of the dimensionality of input and output, I can sample from the common latent space for these two robots.
Okay, thank you. I just wanted to clarify it. Okay, thank you.
Thank you.
So I have one question. So Tuluhan, can you go to the experiments where you show us this marbles? So Yunus, you can also answer my question. First of all, I really like your framework, how you integrate these conditional neural processes to implicitly model the uncertainty. But in all these example cases, as far as I understand, you are predicting like a smooth trajectory. So like for example, for this particular example, what if this demonstration involves more than one action, like first taking a tool and then performing another action? Like in that sense, like you have to maybe have like a hierarchy that multiple steps which involves different neural processes. Does this sound?
So in our classical method, the variance is in the output of the system. So if you have a common demonstration at the start of the demonstration, the common move is made and two different movements are generated. And if you just in the test time condition your system with a point from start, it will generate a distribution with a mean between these movements and variance that shows that these movements are actually not to a single movement. So it also includes variance. So in this case, the first solution we can say that our test time conditions should reflect solutions, should reflect two single solutions. So like if you train these two movements and then you only give this one condition, it naturally fails. But if you give any other condition in the movement, it can distinguish between one of those. The other solution may be, instead of learning variance at the end of the network, we can make the representation space variational, just like in variational autoencoders. So in this case, when you have this observation at the start, instead of a single deterministic representation, you have this variational representations, and when you sample a representation from that distribution, for example, at the first prediction, it goes for one of the movements, and in the second prediction, it goes to the other movement. Like it randomly selects. But in that way, it sort of randomly selects one of the movements. So like, if we have a mechanism to control also that variations, so we can also use that. But in most of the robotic cases, having a mean and a variance is okay for us, because it also says that you can stay on this mean trajectory as long as you are between this variance range. You are safe. Like you can say to your controller to stay on top of this mean, but you can also stay between the variance range.
So basically, my question is about, like, for example, here in all these cases, there are some variations that you capture with different modes. So what if like a condition is the action itself? Then depending on the action, there could be, again, multiple modes. Like I'm imagining this unified framework where you are conditioning on the action, and on this action, again, there could be multiple possibilities that you can enjoy.
So actually, like conditioning on action, like a similar, I think it's similar to observations. So yeah, so here we say that, for example, you should pour a marble, and like we can say this is the action joint angle that you should satisfy. So it's an observation. Let's say like the last time point you should do this. So then like it can produce the trajectory, but like for two different modes. So I think explicit conditionings, like maybe like the blending somehow. So for some time steps, you condition for the first mode, for the first action, then for the second, for like after that specified time step, you will condition to the second action. So I think Yunus had a workshop paper similar to that. And also, as you said, as a future work, that's also in my mind, we can maybe introduce some hierarchical, like maybe hierarchical reinforcement learning or something like that, so that a higher level model will choose what to select for the mode. But like if like implicitly we say there's a trajectory, and like just do it with a single condition, as Yunus said, it's hard for this framework to achieve that.
Okay, thank you.
Just a quick question. In the video, the gripper, is it robotic gripper? The company, is it robot? Okay.
Yeah.
Okay. Thank you again for this nice talk, and I also want to see